Hello, Honors Algebra students. Mr. Lawrence here, and our lesson today is going to be on radioactive half-lives. Now look, half-lives are super duper simple. They really are. First, what is a half-life? A half-life is the amount of time it takes for something to decay. Okay, everything decays. I mean, I think it might be a law of entropy. I might not be positive about that, but everything is wasting away. Okay, so I mean, even a mountain, as soon as it's formed, begins being weathered by rain and wind, and mountains begin to shrink. And given enough time, the mountain won't be there anymore. Of course, that takes a long, long time. Okay, well, substances decay. You know, paper gets old. When we go to Washington, D.C., you're going to have a chance possibly to see the Constitution and the Declaration of Independence, the original ones, and they're going to be under glass and kept in this airtight container vault because they don't want it to decay any more than it has, because the parchment gets really old and it yellows, and then it kind of starts to get brittle, and then it eventually falls away. Those are original documents, so we're trying to keep them safe. Well, when we're talking about a radioactive half-life, that is specifically the amount of time it takes for a substance to decay, for it to go away. You might have heard of carbon-14. Now, I don't believe carbon-14 is such a big deal anymore. I think they have better methods. I have a nephew who just recently got his PhD from Texas A&M, and I don't know that he's working with this. He's actually working for like the Department of Homeland Security or something, so I'm not really allowed to know what specifically he is doing, okay? But I know before he started working for them, he was doing some work on using sugars found in materials to be able to tell the age of something. But I'm not really an expert on that. I don't really know that much about it. But what I do know a little bit about is carbon-14, which is a substance that's in all living objects. And they know how long the half-life is for carbon-14, and so based on the amount of carbon-14 that is remaining when they find something, they can give an approximate date of it. It's really kind of cool. But first, let's do a concrete example of what radioactive half-life is and how you would get one. And then we'll figure out how old something is approximately. So tell you what, let's take sodium here. Sodium-24. It has a half-life of 15 hours. And let's say we had 100 grams at the start, okay, of this sodium-14. I didn't say we have 100 grams of salt, okay? We have this substance called sodium-24, which is probably a little different than normal table salt, okay? And every 15 hours, some of it decays. So at time 0, there is 15 hours, 100 grams. And I'm gonna go like this. I'm gonna put the here. Let's restart this chart. Okay, we're gonna put the time that's gone by, time that's passed. So of course we're starting with 0. Oh, sorry. We're going to put the time at 0. Okay, we're going to put the percentage of the substance that we have, and that's 100%. And then we're going to put the actual amount of the substance. Okay, and let's say we have 100 grams. Okay, now the 100% and the 100 grams won't always be the same thing. I'm just trying to show you how this half-life stuff works. Okay, now we see that the half-life is 15 hours. So in 15 hours later, there's only going to be 50% of the substance, right? And that would mean there'd be 50 grams, okay? Now, a second cycle of the half-life would be another 15 hours, or in other words, 30 hours, right? And then what percentage would be left? Well, half of it, because every 15 hours, half of it is decaying, okay? And that would mean there'd be 25 grams, okay? The next cycle will be 15 hours later, and that would be 45 hours. And now we're talking almost 2 days, right? 48 hours would be 2 days. And we'd be down to 12.5%. Okay? And that would give us 12.5 grams, right? Okay? If I went again to 60 hours, we're not at 3 days yet. 72 hours would be 3 days. We're going to be at what? 6.25. And we'll have 6.25 grams. So you see how that works? That this cycle of the half-life, this tells us the amount of time it takes for half of the substance to disappear. Okay? So you can see something like radium. It takes 1,600 years for half of it to be gone. Uranium, like the stuff they use in like nuclear missiles and things like that, the reason it's so damaging is the uranium just doesn't decay at a very fast rate. It hangs around. And so you have this 4.5 billion years for half of it to be gone. All right, let's do another table, and then we're going to see if we can try to figure out how old something is based on our table. And I'm going to do it very much the same way. So I'm going to have the time. Okay. And I'm going to have, I lost my, it was very strange. Let's see here. Okay. I guess it's telling me I want to use this. So I don't have to keep redrawing them. They won't erase. And we'll need another one here. Okay, so we're going to have the time, and I don't know why I'm making you watch all this. Okay, there we go. All right, so let's do this bismuth, 60.5 seconds. So at time 0, when we're starting, we have 100% of it, and this time, I don't know, let's change the number so that these two don't look exactly the same. Let's say we have, I don't know, 500 grams of it. Okay. Now, after 60.5 seconds, okay, we're going to have 50% of the material, right? Which would mean we'd have 250 grams. All right. Well, excuse me. The next cycle, another 60.5 seconds, what would that be? 121 seconds later, we'll have 25%. And we'd be down to 125 grams of the, which one are we doing? Bismuth 212. I should have named that Bismuth 212. All right. So then another 60.5 seconds. So we're at 180 and 181.5 seconds. We are at 12.5%, and then we will have half of 125, which should be 6250, I believe. All right, and let's go one more cycle. So if I do 60 and we get 241, I think it's going to be 242 on the nose. I could check myself just by doubling this one, right? Yeah, I think so. No, yeah, because it'd be another 121 seconds. That's right. Okay, so then this would be 6.25% left. Okay. And let's say, cut that in half, 62, 26.25. Yeah. Okay. Now, I should be able to determine the approximate age of bismuth based on the amount of the substance that's left. So let's try this. Okay, so I'll tell you what we're going to do. I was just doing a little figure in there. Oh, sorry if there's a break in the continuity. We're going to try to determine how old some bismuth 212 is if we found 78 grams of it in one substance. Okay, it's not like we found like gram here or gram there. We found like a bone and it's got this bismuth 212 in it, and there's these 78 grams in it. Okay, and notice that 78 grams means it has to be between these two times here, 121 seconds and 181 and a half seconds. It's going to fall in between there. So I'm going to use those numbers to help me narrow it down. See how close I can get. Now I won't be able to get like to the exact second probably, but I can get pretty darn close. So we know we have 121 seconds over here, and at that time there's 25%, and there's 125 grams. And then way over here, I know there's 181 and a half seconds, right? And then we're down to 12.5% of the substance remaining. And where are we at here? That would be 62 and a half grams. Okay. Now I'm going to find the median of these numbers. And remember, to find a median, you can just average if there's only two numbers. If there is a lot of numbers, you line them all up and you got to find the one in the middle. But I'm just going to average to find the median. And so when I average 121 and 181 and a half, I end up with 151 and a quarter seconds. And then I average 25 and 12 and a half, and I'm going to get 18 and 3/4%. And then when I average the grams, 125 and 62 and a half, I'm going to end up at 93 and 3/4 grams. Okay. Now the 78 is going to fall in between these two. It's going to be pretty close to being in the middle of them. I think I'm going to go ahead and find the median of this half of the data, or like the third quartile if you're thinking in those terms. Let me do that in a different color. How about purple? Okay, so I'm going to average the 151.25 seconds and the 181 and a half seconds. And when I do that, I'm going to come up with 166.375, and that's really 3/8 in disguise. I mean, that's all that fraction is, 3/8. So basically 166 and 3/8 seconds. Well, let's see how long time it is. Okay, 166, and if we divide by 60, we know it's going to go in twice, right? And so we'll be at 120. Okay, so we're at 2 minutes. 2 minutes something. Okay, and then we have this, 46375. Okay, and so 60 is going to go into this. 5, 6, 7. Yeah, I shouldn't have brought down the 7, 5, sorry. I'm thinking 7 times. 8 won't work. Okay, so 0, 42. Okay, and so we're going to get 437. And again, I don't think 8's going to work, but I think 7 will work again. Okay, and so 420. And then we're going to get 375. And that should be 6. 360. So we're at 150, right? And that decimal is going to go on for a little bit more. But if I think about it, this is a little bit more than 3/4 here. So what's 3/4? 45 seconds. I'm thinking it's going to be like 2 minutes, 45 seconds, somewhere in that ballpark. Not exactly. That's not the answer necessarily. That's what this time is, 166 seconds, right? Okay. Anyway, back to the problem. So now I'm going to average 18 and 3/4 and 12 and a half. When I do that, I get 15 and 625 thousandths of a percent. Okay, and I believe that would be 5/8. That's looking like 5/8 to me. So just a little bit over a half. And then I'm going to average these two. And when I do that, I'm going to get 78 and 1/8 grams. Well, I was looking for 78 grams. So I'm pretty darn close to the answer. Now, if I wanted to, I could keep going. But man, this is so close. For our estimation, I know that the sample of bismuth 212, I believe it was. Is that right? 212? Yeah, bismuth 212 is approximately that amount of time. 166,375 seconds. Now, it's okay to give it that way because the half-life is given in seconds. Although, if you've got somebody reading it, you can say, or about 2 minutes and 45 seconds. Now, you know, I'm just kind of curious here. Hold on one second. Put up my calculator, and I'm going to try to get that even closer. We'll see how close I got. Okay, I took 166.365, 166.375, I believe, and I divided it by 60. Okay, this will get me minutes, right? So I got this 2.7729 number. I might even have mistaken my long division. Apologize for that if I do. Right, so I know it's going to be 2 minutes minus 2. Now I'm going to multiply by the seconds by 60. And there I'm at 46 1/8 seconds. So my estimation of 45 was pretty close. I guess if I wanted to be accurate and use my calculator, that could even be a better way to do it. So really, 2 minutes and 46 seconds would be even better. You know, when we're talking seconds in half-life, that matters. If we're talking billions of years in half-lives, like in the uranium, you know, a second, what's the big deal? So you got to consider the context of the problem. Hey, let's try another one. Hold on one second. Okay, so I looked up the half-life of something called polonium-209. Its half-life is 102 years. And we're pretending we're archaeologists or scientists, and we just found a sample of it. We know there's 90% of the substance left. Can we find the approximate age of it? Well, sure we can. First of all, we know that at 0 years, right, because our time is years now, there's 100% of it left. And yeah, I don't think we need the grams in it. We'll just use the years and the percent because the grams aren't mentioned, so that's not relevant. Okay, and then we know that in, I'm going to put it way over here, that in 102 years, there's 50% of it left, right? I don't need this chart to go past greater in time than 102 years because I'm considering 90%, and 90 is between 100 and 50, not in the middle, but between. Now let me find what's in between here. If I average 0 and 102, I believe I'm going to get 51 years, right? And that would mean there was 75% left. Not 25%. 25 would be over here. Remember, I have to average them. So I add 150 and divide by 2. Okay, well, 90 is in between these two. So let's see how many years are in between here. 25 and a half, right? 25 and a half years. 25 years and 6 months. Okay, and that would take me to 87.5%. So the 90 is going to be between these two. Now I may blow this up a little bit because I'm not sure where I'm going to be 100%. And I'm going to move the 25 and a half years here, and that'll get me at 87.5%, right? So now I'm going to average these two and have that. It should be 12 3/4, I think. Yeah, 12 3/4 years. So 12 3/4 years. And what percentage am I at? Well, 187.5 divided by 2 is 93 3/4. So I'm getting close, but I can get even closer, I'll bet. So now I'm going to average these two. So I'm going to have 12 3/4 plus 25.5 divided by 2. And that's going to get me 19 1/8. Oops, that should be a 5 there. Sorry about that. Okay. and then I'm going to average the 93.75 and the 87.5. Oops, made a small mistake, sorry. Okay, and I'm going to divide by 2. And, ooh, look at that. I'm at 90 and 5/8. That's getting pretty darn close. You know what? I think I'm going to go with this one here. And I know it's going to be a little bit longer than this answer. So if I have 19 years, right, and I have 0.125, well, I don't know what 1/8 of a year is, so I'm going to multiply 0.125 times 12. Okay, well, that'll be 1.5 months. So if you count a month as 30 days, you can say 19 years, 1 month, and half a month would be, you could say 2 weeks, you could say 15 days, because months tend to be about 30. So I'll say 15 days. And of course, this is only an approximate answer. Now, if you want to see how I did that, all right, I've got the 19, here, let me clear all this off. I've got the 19.125, right? Okay, I know that's years, so I subtract off the number of years. Now I'm left with the decimal or the percentage of a year, so I'm going to multiply by 12. This will tell me how many months. Okay, now I'm at 1.5 months. So I'm counting a month as 30 days. I subtract off the 1, so I've got 19 years, 1 month, and then half times 30, or half of 30 is 15, and that's how I did that. All right, this is some pretty cool stuff. You're really starting to see how the algebra can be used in the real world. And you've heard people say, well, we never use algebra. No, people choose to never use algebra. People complain about going to school. You know who complains about going to school? People that don't want to be educated. I mean, that's the bottom line. And if you're educated in this world, you have a much better chance at a more rewarding, fulfilling life. Okay, now if that's not a goal for you, like if you don't get a reward from your work, like I have some respect for people who are missionaries, you know, they're not worried about, you know, getting a tech job and this and that. They get rewarded by serving other people. Wonderful, great, but many people wish to go and get a decent job and make a certain amount of money. Well, you need an education for that. And yeah, is it a pain in the butt to get? Oh yeah, but if you work hard on this end of your life, it'll be easier on the other end of life. I mean, I've heard so many people who are so much older than me tell me that. I totally agree with it. All right, I'm done preaching. Mr. Lawrence signing off. Have a good night, everybody.